Hey everyone and welcome back to PrepFusion. I'm Anish and today we will start the lecture 5B of our Electrostatics chapter. So in the previous lecture we learned about electric potential energy. Then we learned about boundary conditions between dielectric and dielectric interface. So today we'll do mainly questions, assignment questions on dielectric boundaries, and obviously we'll do the other condition, that is dielectric conductor boundary. So I gave you a simple homework, this question as homework in the previous lecture. So we'll solve this first and then we'll obviously solve today's lecture's questions as well. So we have two mediums, z greater than 0 z less than 0 and z greater than 0, and in medium 1 my relative permittivity is 2.5 and in medium 2 relative permittivity is 5. Electric field in medium 1 is given. I have to find out the electric field in medium 2. Pretty simple, straightforward. Okay, and mostly questions like this will only come. I will show you a gate P by Q as well. They're exactly did to this question. This type of concept has came up. So what is the surface for z equals to greater than 0 and z less than 0? What is the surface? It is basically the xy plane, right? So if this is my xy axis, xyz, and this is basically my xy plane. So what is the interfacing media? Interfacing media is this, right, at z equal to 0. So z equals to 0 or the xy plane is interfacing medium. Surface. Medium 1 is what? Medium 1 is z less than 0, so below. So this will be a medium 1. Here my epsilon r1 is 2.5 and this is my medium 2. My epsilon r2 is 5. Okay, epsilon r2 is 5. So these are my medium 1 and 2, and basically now I can segregate my tangential and normal component. So like from this electric field, can you identify what is the tangential component and what is the normal component? So here normal to what? Normal to the surface, normal to the interfacing medium. So intuitively I can say what is the normal direction? Normal direction will be in this direction, right? V greater than C. V greater than C. What it is increasing. So this will be the normal direction, that is AZ cap. So in AZ cap, what electric field I have? Simply only this, right? So En1 normal will be AZ cap only, right? This is the only normal direction electric field that I have, volt per meter. Now if you don't want to do it, if you want to do it with simple formula, like that is not formula, that like we have derived it only. So you simply do what? You do E1 dot the normal to the surface, interfacing surface, that is AZ cap. This will give me the component En1, which is equal to what? If I take the dot product with AZ, what will I get? This will be 0, this will be 0, this will be 1. So only I get 1. And the normal component will be in the direction of normal, normal to the surface itself. So it will be AZ cap. Simply AZ cap, right? So that is the case here. So what will be the tangential? Tangential will be the part that is not present of the normal component. So ET1 will be simply E minus E1 minus En1, which is basically this 4ax plus 2ay cap. Okay, 4ax plus 2ay cap volt per meter. Okay, so this is the case here. This is the case here. So from this I can say, what can I say? What was the tangential component relationship? ET1 should be equals to ET2. Correct? Right? So if both of them are same for a dielectric interface, so I can say that ET2 will also be equals to 4ax plus 2ay volt per meter. Okay, and what will be the normal component? Okay, normal component, I have to add a page. Like I'm just wasting time here. I can do this in seconds, okay, in one line only, but we have to do it step by step, so I'm going step by step. So the normal component, if you remember, the flux density like you can use a Gaussian surface here, take a Gaussian surface here as well, and then you can write down the like Gauss law. You can derive, but like it is totally understandable, right? D1 is in this direction, dn1 is in this direction, and dn2 is in the same direction. And nothing is they have told, and they haven't told anything about the interfacing medium. So I will assume that it is a charge free region. Okay, assume rho is to be 0 as nothing is mentioned. If something was mentioned, they would have definitely said if rho wasn't 0, right? So dn1 is equals to dn2. That means what? If I break this down, that means epsilon r1 equals to en1 equals to epsilon r2 into en2, correct? And what is epsilon r1? It was 2.5. en1, I do know what is en1. En1, just hold on, en1 is 1, okay, volt per meter, and epsilon r2 is 5, and en2 I have to identify, that is unknown to me. So en2 will be simply 1 by 2 voltmeter, and direction will be in the az cap direction. So overall my E2 vector will be ET2 vector plus En2 vector. So ET2 vector is what? ET2 vector is this, right? 4ax plus 2 ay cap, and En2 vector will be 1 by 2 a z cap. Okay, so like how can I do this in a fast manner, like in a simple manner? Like just like see the question and just say the tangential component will be same. The what is the normal to the surface, interfacing surface, they have given az cap. So az cap I have to remove, and this will be the tangential component. It will be same as the E2. So it equals to 4x plus 2ay. Done. What about the normal component? Normal component, I know that the flux density series difference should be equal to the charge present on the surface, right? Rho s, charge density. As nothing is mentioned, rho s is 0. So the normal direction of the flux density should, both of them should be equal. That is epsilon r1 into en1 equals to epsilon r2 to en2. What is the en1? That is 1. Okay, because in the normal direction I have only 1 volt per meter. Everything else will be ignored. So 1 into 2.5 equals to 5 into en2. So it is 2.5 by 5 equals to en2, that is 1 by 2. So en2 is 1 by 2 az cap, and all other components are same. So I got my E2. Okay, so like just verbally you can do, orally you can do, as this is the first time I'm solving this question in front of you, so I'm going slowly, but you can do this verbally, and these type of questions actually do come in the examination. Okay, it's not like these type of questions don't come. These type of questions do come in the examination, and I will show you the live example, this GATE 2015. Now can you solve this question for me? Just same ditto question. Okay, same ditto question they have given along a uniform electric field. Region 1 has electric field this, and the interfacing surface is y equals to 0, and you have to identify the electric field in the region 2. Same ditto question. Can you do it for me? This is the homework for you. Just a question that I solved previously, right? It's the same as this question, nothing different. Okay, just same. Now a parallel plate capacitor like this, we are like, you might say, sir, we haven't studied capacitors, how will I be able to solve it? Yes, you will be able to solve it without even knowing capacitors. You will be able to solve it. Just understand it as 2 sheets of paper. A parallel plate capacitor filled with dielectrics is shown below. If the electric field in the region A, electric field is 4 kilovolt per centimeter, then the electric field in the region B will be. Okay, so one thing you have to understand is that in this boundary, right, electric field between two capacitors, like they if you know a bit about basics of capacitor, that's fine. If you don't know, don't worry, I will just explain all this in capacitor separate, don't worry. But one thing I know is that the electric field, these are the 2 plates, right, and the 2 plates are always charged, and electric field, let's assume any charge, right, let's assume electric field is on the other, one side I have positive and other side I have negative charges. So electric field will start from this and terminate here, right? If you know anything about capacitors, you know. Or what you just assume this to be uniform sheet of paper, and this to be not paper, sorry, anything uniform sheet, and these two are, this is also uniform sheet. Okay, and both of them has equal charge densities. So what will be the electric field in between? Electric field in between will be the twice of this, because I have shown something similar configuration. If you remember, if I have 2 infinite sheets, and in between what is the electric field? These type of questions we have done hundreds of times in the previous few lectures, right? So that should not be a doubt to you that this between electric field should be sigma upon epsilon. Outside what should be electric field? This outside what should be electric field? You decide. Okay, it should be 0, correct? If this is plus and this is minus, okay, this is plus and this is minus, then it should be 0. But inside it should be double, basically, not sigma upon 2 epsilon. It should be sigma upon epsilon. This I know. and here I have a boundary. And along boundary, what information I know? Along boundary, the information that I know is the tangential. Like this is the tangential component, right? This is the boundary, and this is the tangential component. I don't have any normal component. So basically, this electric field has only tangential component. So ET1 should be equals to ET2. And what is ET1? ET1 is simply 4 kilovolt. So ET2 also should be 4 kilovolt because it doesn't have any normal component. So E2 will also be 4 kilovolt as En2 is 0. Okay, doesn't have a normal component, it's just a tangential component, right? This is the surface and I am tangential to this. Normal means this, right? Normal means in this direction. It's not normal. So it will be same as 4 kilovolt only, it will not change. Okay. So if you couldn't understand this question, don't worry, we'll go when we'll solve capacitors, they will understand. But the students who can understand this, right? Like basic concept of capacitor is already cleared. Basic concept of capacitor is already clear. This is the place from where we start studying the capacitors. Okay, so it will be same as 4 kilovolt per centimeter. If you couldn't understand, don't worry, this will be clear. Just write down in your notebook that I will understand this in capacitors chapter. Okay, so yeah, let's start the next question. This question is actually pretty good. Okay, so here I have a surface, okay, infinite sheet of paper with surface charge density as 2 coulomb per meter square. So and this is the medium one. Medium one is this is the interface, right? This is the interface actually. This is the interface. Okay, and in medium 1 my epsilon r1 is 5 and medium 2 epsilon r2 is 2.5. Can you tell me the electric field on medium 2? So for this, first of all I have to write the electric field on medium 1, then I will write the electric field on medium 2 and equate the tangential components and the normal components. This is, I will assume this is charge free because they haven't mentioned anything to me. So what I will do, rho s is like this. Okay, if I have a sheet of paper like this is infinite sheet of paper, right? This is infinite sheet of paper. Okay, this is infinite sheet of paper. So here what can I say is that this angle is 30 degrees. So with respect to the normal, what will be this angle actually? What will this angle? I don't know. But I know this angle is what? This angle is 30 degrees, right? So actually this angle, this is the normal. Okay. And this angle is 30 degrees actually. Same as this angle, right? Same as this angle. This angle and this angle will be same because these sides are basically parallel and this is on the surface itself, right? So this angle will always be 30 degrees. What about this angle? This is the normal to the surface, right? Normal to the surface. So this whole angle is 90. This whole angle is 90. So this angle will be what? 90 minus 30 equals to 60 degrees. So actually I know what is electric field in this direction. The electric field in this direction will be what? It will be sigma s upon 2 epsilon, right? Sigma s upon 2 epsilon and rho s upon 2 epsilon. So along this and along this, right? This is the ax direction and this is the minus ay. Okay, I will just write down the coordinates. So I will assume this as ax and this as ay. Okay, so actually my electric field in the interface 1, right? Electric field in the interface 1 will be rho s upon 2 epsilon will be there obviously. Cos 60 cos 60 in the ax cap direction plus sin 60 in the ay cap direction. Okay, so I know what is rho s. Okay, I know this. So this I have got. This is my electric field. Now from here, can you tell me what is the tangential component and what is the normal component? Normal component will be, this is the y equals to 0 surface again, right? So ay cap will be the normal component, right? So my en1 will be, this is sin 60 means root 3 by 2. This will be root 3 by 4 epsilon into rho s ay cap, and et1 will be rho s by, this is sin 60 means 1 by 2 4 epsilon Ax cap. This will be equals to my ET2, right? This will be equals to my ET2. But what about my EN2? I know again charge free region, so dN1 will be equals to dN2. Nothing is mentioned, so rho is equals to 0. Okay, charge density on the surface is 0. Okay, so if charge density on the surface is 0, what can I say? I can say that this rho is by 2 epsilon is 0, right? So this I can say is epsilon r1 into En1 should be equals to epsilon r2 into En2. Epsilon r1 is how much? Epsilon r1 is 5 into En1. En1 is what? En1 is this, right? Simply this. Rho is 2, so this becomes root 3 by 2 epsilon equals to this 2.5 into En2. So En2 will be equals to root 3 by this actually comes out to here I have epsilon r epsilon naught actually. Okay, this actually cancels out. Remember here I have epsilon r as well, right? Epsilon r epsilon naught. Okay, one thing has changed here. Just hold on a second now. This is epsilon r1 itself. This actually becomes independent of epsilon r, I think. Electric flux density will be same only. Epsilon r2. Okay, this actually doesn't become independent. This cancels out. Epsilon r cancels out. And this epsilon r1 will actually go in the bottom. So this will be epsilon 2. This will be, yeah, epsilon 2 of this particular electric field. Okay, so what can I say? Actually, can I say this in terms of rho s or something? Rho s, we just hold on a second now. Just hold on a second. So epsilon, this is epsilon r naught e naught. So what is my, like, what is my En1? En1 is, just hold on, this particular thing, right? It is actually, this should be actually epsilon 1 epsilon 1. This I have confused with it. So this is epsilon 1. Yeah, we'll not confuse. We'll just keep it epsilon 2 only. Just keep it epsilon 2 only. That will be simpler for you. Okay, we know what is epsilon naught and epsilon r2 is given, so I can directly put the value of that. I will get my results, right? And so basically what will be my electric field? This is in the normal direction plus ay cap direction, correct? So my electric field in the medium 2 will be, tangential component will be same, this only, rho s upon rho s is 2, so this becomes 1 by 2 epsilon 1 ax cap plus this is root 3 by epsilon 2 ay cap. Okay, so this is my electric field in the second medium, and this will be the answer. So this is a very good question actually. Please rewatch it again, how I derived everything, step by step procedure. Okay, let's move on to this next question. This question is also pretty good. You can do this. This question have told us that a surface shown below is lying above the origin, acts as an interface medium between two mediums. Medium 2, now this surface, right, which is lying above the origin, is acting as an interfacing medium between two mediums. Interface between two mediums. Medium 2 resides below the surface, so medium 2 is somewhere below this, and medium 1 is somewhere above, also mentioning that it is near the origin. Medium 2 is near the origin and medium 1 is away from the origin. Find the angle made by the electric field of medium 2 with respect to the normal. Okay, normal of the surface with respect to normal away from the origin. Normal away from the origin of the surface. Okay, like there can be two normals of this surface, right? Like obviously any surface can have two normals if it is not enclosed, if it is not a closed wall. So this can be a normal, okay, and this also can be a normal, right? But it is telling find the angle with respect to the normal away from the origin, not towards the origin, right? So I will find the normal here. How will I find the normal here? That also I will explain. Don't worry about that. So this is one thing. And find the energy density present on medium 2. that also will derive basically. So first of all, how do we find out the normal? That is the first task, right? That is the first task. Find normal. So task 1 is find normal. There are two methods to finding normals of a like unknown surface which is not given. Method 1 is simple. Grad phi, right? An cap will be grad of phi divided by magnitude of grad of phi. Where phi is greater than 0. Correct. So how will I solve this basically? I can find out the equation of this like tetrahedron, like not tetrahedron exactly, but these type of structure we have actually found out the equation of this. This is like a plane. Equation of a line. This is in the yz plane. This is just a line, right? And how do I write the equation of a line? Simply, I can write it like this. Like let's take xy for example. If I take xy for example, equation of a line I can write x by 2 plus y by 2 equals to 1, because if I put x equals to 2 here, I will get 1, and if I put y equals to 2, I will get again 1. What I am trying to explain, I will say, I will just write this down. X by 2 plus y by 2 equals to 1, right? How is this equation of line? You can do that y equals to mx also. You can do like this as well, okay? So here x by 2 is the intersection with the x axis, y by 2 is the intersection with the y axis, and 1 will just stay over there. So what happens is, if I put x equals to 2, I will get what? I should get what? I should get 1, right? Why I should get 1? Why you should get 1? Just hold on. This should be, oh sorry, if I put x equals to 2 and y should be equals to 0, yeah, I should get 1, which is satisfying here. Now if I put here x equals to 0 and y equals to 2, if I put x equals to 0 and y equals to 2, I am getting this left hand side is 1 and right hand side is equals to 1, so it is satisfying. Now same, if I do it for the z plane as well, it will become z by 2, because this is symmetrical, and here also it is intersecting 0, 0, 2, so that's why. But if you like couldn't find out the plane, right, I will tell you an alternative as well, if you couldn't find out this equation. Okay, so from here what I can say is, if I take this on the left hand side, plus minus 1, now if I increase these values, just if I increase x, y and z, make this greater than 0, like if I let this equals to phi, and if phi is greater than 0, that means I am going away from the origin. If you observe x, y and z all are increasing, I am going away from the origin. If this is less than 0, then I am going towards the origin, but I need the normal away from the origin, so I will assume this as greater than 0 only. I will not assume minus phi, I will assume this greater than 0. So now I will find the gradient of this, so that I will get the normal vector. So the gradient of this will be En cap will be simply grad of phi divided by magnitude of grad of phi. So what is grad of phi? Simple, everything is ax, 1 by 2 will be outside, this will be ax cap plus ay cap plus az cap, okay, divided by the magnitude. What is the magnitude of this? Like 1 by 2 will be anyways outside, it will be under root 3, correct? So this will come out to be ax plus ay plus z under root 3. Okay, this will be the En cap direction. Now what if you tell me, sir, I couldn't understand how you write the equation of the plane, but although we have learned this in integration chapter, but still if you couldn't understand, we have other method as well. What is the other method? So whenever you have to find the normal to a particular surface, right, you can write the two vertices, or you can write down the expression for two surfaces, two sides of the surface, and then take the cross product of that and divide it by its own magnitude, and you will get back the same vector. So let's name these things ABC. So let's name a vector AB and another vector BC. So if I take AB cross BC, right? AB cross BC, what I will get? I will get a vector normal outward, going outward from the origin, right? If I would have done AC cross CB, I would have got like a vector that is going inwards to the origin. So please do it hands on, try it out yourself, then you will be able to understand what I am talking about. So if I do AB cross BC, what will I get? I'll do AB cross BC, right? So what is AB? Like, I know how to write position vectors in Cartesian coordinates, right? Most simplest thing. So AB will be OB minus OA. This is equals to what? OB is what? 2AY cap minus OA is what? 2AX cap. So this is my AB vector, right? This is my AB vector, and my BC vector is OC minus OB. Okay, so OC is what? OC is this, right? AZ cap in the AZ cap direction minus OB is what? OB is in the AY cap direction, correct? So I will just take the cross product of these two. So AB cross BC will be what? I hope you haven't forgotten how to take the cross product, right? In the Cartesian coordinate system. This is not IJK, sorry. This is AX cap, AY cap, AZ cap, and AB is minus 2, 0 and 0, and BC is 0. How is this minus 2x? This should be minus 2, sorry. Okay, I messed up. This should be 2 and this should be also minus 2, right? Okay. Yeah, minus 2. So this should be actually, there should be 2 minus, sorry, minus 2. This should be 2 actually, not 0, sorry, 2, and this should be 0 minus 2, 2. Okay, so now I can take the cross product simply. What will the cross product? AX, this is the AN cap vector. I have to divide by the magnitude as well. I will divide it by magnitude, don't worry. Will be equals to AB cross BC divided by magnitude of EB cross BC. This will be equals to AX, this is 2 into 2, that is 4 minus 0, so this will be 4 only, minus AY will be here outside, this will be minus 4 and 0, so this is minus 4 plus AZ, this will be 4, correct, and divided by the magnitude will be what? 4 will be common in US, 4 root 3. So this will come out to be AX cap plus AY cap plus AZ cap divided by root 3. Now isn't this the same expression that we derived previously as well, right? So you can do it both ways. If you ever forget that, like the first method, you can do it in the second method. Okay, so this is bit simple. Now we have to do the simple thing only. Now we have to find out the angle made by the electric field of medium 2. So first of all, the electric field in medium 1 is given. So this is E1 actually, and I have to find out the electric field in medium 2. Okay, I have to find out the electric field in medium 2. For that I have to first of all write down the expressions of electric field in medium 1. So what is En? Like E1, basically E1 is 4AX, I think 4AX minus AY plus 2AZ. 4AX minus AY plus 2AZ. Okay, so this is the electric field in the medium 1. What about En1? Now things are not simple. Now things are not that obvious that you can directly observe this E1 and say what is my normal component. What you have to do? You have to go by the basics. What to do in the basics? Basically, take the dot product with the normal vector, right? So if I take the dot product of normal vector, it is AX, AY, AZ by root 3. So 1 by root 3 will be outside, and simply 1 will get multiplied to 1 minus this is the magnitude of the normal component, basically 4 minus 1 plus 2. So this actually becomes 3 plus 2, 5 by root 3. Okay, and your normal component, electric field in the normal component will be En1 vector will be magnitude of En1 and En1, right? an, not n1, basically an vector. So this will be equals to 5 by root 3. Already I have 1 by root 3 extra, so this will become 1 by 3 ax cap plus ay cap plus az cap. Okay, so this is true. So this, I get the electric field in the normal direction. So from this, can I find out the tangential component? Yes, definitely. So it will be just E minus En1. This is not that straightforward. You have to identify the surface that equation and all. So this will come out, we have to subtract from the main electric field E1 to get the tangential. So 5 by 3 minus 4 minus 5 by 3. So it will be 12 minus 5 by 3. So it will be 7 by 3 ax cap direction. Then minus 1 minus 5 by 3. So it will be minus 8 by 3 a y cap direction. Then 2 minus 5 by 3. So this will be 6 minus 5. So 1 by az by 3. Okay. So this is the case here. So my can I say what is the electric field on the tangential component of the second medium? That will be same. That will not change. So this will be exactly same as ET1, which is this, correct? Simply this. So what about the normal component now? What about the normal component now? So normal component, I know one thing, right? That again nothing is mentioned about the charge in the mean this surface. They haven't mentioned anything. So assume rho s to be 0. dn1 minus dn2 equals to rho s equals to 0. Okay, assume nothing is mentioned, so you will assume this only. Now obviously dn1 will be equals to dn2, so basically my epsilon r1 into en1 magnitude will be equals to epsilon r2 into magnitude of en2. Okay, so magnitude of en2 will be what? It will be magnitude of en1 divided by this, and obviously there is a normal vector, that's a different matter. So magnitude of en1 is simply this, right? 5 by root 3, 5 by root 3, and epsilon r1 is how much? Epsilon r1 is simply 2.5 and this is 5, so it will be multiplied by 5. Okay, so 2.5 by root 3. Okay, so this will be the magnitude in this direction, and obviously my en2 will be what? Magnitude of en2 and obviously the normal vector, correct? So if I just write down the normal vector, it is also ax, ay, az divided by root 3, so it will come out to be 2.5 divided by 3 ax plus ay plus az, correct? So now I have got en2, en1, et1, et2. So my electric field in that electric field in the second medium, I can directly write what it is equals to en1, en2 plus et2. So what is my en2? So my en2 is this, right? En2 is this. If I just come back here, what was I? This one only, right? en2 is this only. So I'll write, copy and paste this here. And what is my et2? Et2 I have just derived here itself, which is same as et1. So this one, if I just add things up, this one will become 9.5 by 3 ax, and minus this one will become, this is 5.5 by 3 ay. Okay, and plus 3.5 az by 3. Okay, plus 3.5 az by 3. So this one becomes E2. And now I will take the dot product so that I will be able to understand the angle. How do you find out the angle? Just take the dot product with a normal vector from with respect to which you want to find out the angle. So my cos theta I will get by E2 dot an cap and divided by magnitude of E2, because like an magnitude is simply a 1, right? So this one will come out to be what? This one actually will come out to be 1 by 3 I can take in common, and it is ax ay plus az, so this will be 9.5 minus 5.5 plus 3.5 divided by, and don't forget there is a root 3 as well. Okay, there is a root 3 as well, don't forget that. And again 1 by 3 will be common here only. Okay, like you can do it by yourself. I'm just doing it directly. You can do it by yourself. You can cross verify. And this magnitude will be interesting. 9.5 whole square plus 5.5 whole square plus 3.5 whole square whole under root, right? So from this my cos theta will be what? Cos theta, will just quickly write the things down here. This will be 9.5 minus 5.5, so this will be 4. And this is 4, and this is, if I just add 3, it will be 7.5. So 7.5 divided by root 3. Okay, this is 4.33. Okay, 9.5 square plus 5.5 whole square plus 3.5 whole square under root, so it will be 11.52. okay, it will be 11.52, and if I multiply this by 4.33, I will get 0.376. 0.376. So what will be my theta actually? Theta will be cos inverse of this. Okay, it is 60. Just keep in mind it is not coming negative, so angle will be a acute one, right? So it will be come out to be almost 68 degrees, right? 67.93 degrees. So this will be the answer basically of this particular question, 67.93. So the electric field in the second medium will make an angle of 67.93 angles degree with respect to the normal. Okay, so this is a good question. This you can star mark this one and again try by yourself later on at a later stage. Now you have to find out the energy density present on medium 2. How do you find out that? So for energy density, right, we know a formula, and that this one I will recommend you to remember. Okay, no need to do any magic things here. I know energy density formula is half. Just remember the simple formula, right? Epsilon 2 into electric field magnitude whole square, or I can write this as half this permittivity, okay, electric permittivity, and magnitude of d2 whole square. Any one of them will work. Any one of them will actually work. So this will be 1 by 2 epsilon 2. So like I know what is half. I know what is epsilon 2. Epsilon 2 is epsilon naught into epsilon r2. So epsilon r2 is I think 5. I believe it is 5, right? Yeah, it is 5. So 5 into epsilon naught is 8.854 into 10 raised to the power minus 12 into the electric field whole square, magnitude of electric field. Magnitude of electric field is what is the magnitude of electric field? This is the magnitude of electric field, right? This I have to just divide by 3 and I will get back the magnitude of electric field. If I divide this by 3, 11.11.52 divided by 3, 3.84. So 3.84 is actually the magnitude of electric field, and I have to do the whole square. So what does this come out to be? Whole square into 8.854 into 5 divided by 2, 326.4. and if I just take this 10 raised to the power more minus 3 inside, so 0.327 nano joules per meter cube. So this will be the energy density basically for the particular electric field in the medium 2. So pretty straightforward and simple question. Just the second part is formula based, first part is conceptual based. Okay, so can you, like, this is just the same question only. Just here I've given you the equation. Okay, I've directly given you the equation. Can you solve it for me? Can you solve this question? So this question will also be the homework for you. I know you can solve this. Okay, try to outdo yourself. I won't solve this. Every question I won't solve. Few questions you have to solve, right? So like this is pretty straightforward. Just it can be a bit lengthy. Okay, and in the next lecture, not next lecture, basically in this question also I want you to try out and by yourself. So there are two extensive homogeneous isotropic dielectrics meeting on a plane z equals to 0. So z equals to 0 is basically the interfacing media. And epsilon r1 is given, epsilon r2 is given, uniform electric field is given, exists for z greater than 0. So you have to find out the E2, the angles between E1 and E2 that make with the interface. So with respect to normal you can compute. I will compute all this in the next lecture, don't worry. Energy densities in both dielectrics, the energy within a cube of side 2 meters centered at this. Okay, this also we'll see how we will solve this. Okay, this question is also very good. This part you can solve it by yourself, and in the next lecture I will solve. Okay, so let's come, like there is another interesting question, that's why I am like doing this, giving you this homework. Okay, this question is pretty interesting. We have to find the electric field in the medium 2 if the surface charge density present on the surface is 10 epsilon naught. So because up until now they haven't mentioned anything about the surface charge density, right? Okay, there isn't any surface charge density, but we have to do a question with surface charge density as well, so that you have a good grip on all of the concepts. So now this medium, I know medium 1 is z greater than 0, medium 2 is z less than 0. This is fine, but there is surface charge density on the interface medium. Okay, so I will just write down the planes, x, y, z planes. So this is my x, y and z plane. Okay, z equals to 0, right? Yeah, z equals to 0. X, y and z. Okay, and this is z equals to 0. So what I can say, that here my surface charge density rho s is equals to 10 epsilon naught. Okay, 10 epsilon naught they have given me. Fine. Now what I have to do? So basically now, right, you just be a bit cautious. So you solve it by yourself. This is like z greater than 0 is the medium 1. So this is the medium 1. And this is the medium 2. Okay. And what else can I say? I can say that this is my E1 and epsilon R1 is 2.5. Correct? 2.5 and epsilon R2 is 5. And what is E1? E1 is 2ax plus 4ay plus minus 2az. Minus 2az. Okay. So this is my E1 and E2. So I have to find out the electric field on the medium 2 basically. Find the electric field on the medium 2. So from here I can write down the expressions. So I will write this, I will have this as my reference normal direction. Okay, this is my reference normal direction, dn1 and dn2. Now I don't care if dn1 is actually in this direction. I will write this in negative. Okay, I will write this in negative. So my E1 is this, right? 2ax plus 4ay minus 2az. Now obviously you can see the expression and directly say what is my En1. En1 will be with the direction minus 2az cap, right? It is negative, that is fine, but my reference I will take as this to remove all the confusions. Okay, and from this I can do the normal condition, right? Normal condition, apply the normal boundary condition. What is the normal boundary condition? I will just take a small cylinder, and this is dn1 and this is dn2, right? So I will just do this. Dn1 minus dn2 will be the net flux that will be residing inside the surface, that is surface charge density rho s. Okay, so from here I can derive few things. Now dn1 actually is negative. Dn1 is actually in the negative direction. Okay, so I will write here minus 2. I will write here -2 because dn1 is actually the negative direction. What do I mean by this? So like this, right? Actually, what was the actual formula? I had to take a dot product with this, right? With the surface vector. Surface vector I have assumed this direction. So reference surface vector I have assumed this direction. So which is positive az cap direction. Okay. So now we'll write everything very carefully. This will be epsilon 1 into dn1. What is dn1? Sorry, epsilon 1 into en1. En1 is -2 az cap. Minus dn2 I don't know. Okay. dn2 dot az will give me what? Just the magnitude. dn2 dot az will give me just the magnitude. Right? Magnitude of dn2 in the positive az2 direction. Positive az cap direction. Which is equals to rho z, which is 10 epsilon naught, right? Just 10 epsilon naught. So I can directly write here what will be the magnitude of dn1. Now can I write this in electric field? So dn2 will be epsilon 2 into epsilon naught epsilon r2 into e2. Okay, so this will be here, right? I have forgotten to take a dot product. Like this whole thing is with dot product, right? I have forgotten to take that. This will be dot az cap. Epsilon naught into epsilon r1 and magnitude. This will be 2 only. Okay, and obviously this is minus 10 epsilon naught. Okay. So this I will actually get back with the proper direction with respect to the reference direction, correct? So this one I will divide by everything. So this E2 magnitude, right? Although this can't be negative, but this is with respect to the reference direction. So yeah, I like better. Yeah, this I can write, and this one will come out to be epsilon r1 is 2.5. So this will be 1 by 2 into 2 minus 10 divided by epsilon naught will go away and 5 will be still here. Yeah, this is correct, by 2. So this will be -1 -2, so -3. Now how can magnitude be negative? Like what is this telling us? What is this negative sign is telling us is a direction. Okay, this negative sign is just telling us a direction. Magnitude can never be negative, right? Direction means this will be in the minus az cap direction. Okay, so my E2 actually will be in this direction -3 az cap. Okay, so E2 will be -3 az cap. Now like I know many students will get confused in this. Please don't do everything systematically, so you will never get confused. Do everything from basics, correct? So now I can simply find the tangential component. Tangential component will be same as the tangential component of the medium 1, right? Medium 1. So ET1 is basically equals to 2ax plus 4ay. 2ax plus 4ay. Okay, and my En2 is minus a 3 az cap. So my electric field in the medium 2 will be simply 2ax plus 4ay minus 3 az. Okay, so like I know like we solve it just without any stutters or something, but when you will try to solve it by yourself, right, you will face a bit of problem. So for this only I took this question for this particular thing. Okay, for this particular thing I hope there is no confusion here, right? So now we'll learn about the perfect conductors. Things will be even simpler than the dielectric condition. Why I will explain. So let's read this particular statement. Here they have told us, just hold on. Yeah, here they have told us, at boundary between a dielectric and a conductor, the tangential component of the electric field inside the conductor is 0. The tangential component of the electric field inside the conductor will always be 0. Okay. Now if the tangential component inside the conductor will be 0, that means the tangential component of the second medium, right, will also be 0. It will have only normal component. Why is that the case? Why is that the case? Why is the tangential component 0? I can talk all these things are there. All these things we already know. This normal component will be same. Okay, this normal component proof will be same as the previous component. Just this new relation you have to know that tangential component will be 0. It has become even simpler. Now why is the tangential component 0? Why is the tangential component 0? Let me take a simple spherical conductor, right? Now if you remember a spherical conductor, if it is a sphere, the electric field is always radially outwards. Okay, always radially outwards. Now is there any tangential component here on the surface? Is there any electric field in this direction? No, right? There is not any electric field in this direction. And what is the reason for not having electric field in this direction? I will tell you that as well. That as well. Now here if you observe, okay, where did it, okay, this thing didn't go here. So here if I observe that if I have a simple surface here, right, like simple conductive surface, okay, this is not a sphere, not a symmetrical surface, just a surface. Now if there is some tangential component, let's assume there is some tangential component ET. Okay, there is some tangential component. If there is some tangential component, what does that means? That means this positive charge will actually feel a force in the direction of the tangential component, right? So it will try to go in that direction. Correct? It will try to go in that same direction. So here charges will move. This charge will move. This charge will move. And what will happen? A closed loop will be formed, right? Closed loop will be formed. And if closed loop is formed, current flows, right? I is not equal to 0. But can current flow like this anyhow? Like this is a conductive surface, right? This is simply a conductive surface. Can current flow through this? Through the outside thing? If nothing is present, right? If no extra circuitry I am not giving, can current suddenly flow? No, right? They cannot certainly move. So that's why, like I have just shown you practically as well, why the tangential component will not be present. Why it will be 0? Okay, that's the reason. So now, like basic field boundary condition is there, right? That is always true, that tangential components on the medium on the surface interfacing surface will always be equal. So if this tangential component across the medium 2, that is the conductor, is 0, then medium 1 tangential component will also be 0. That's why this is 0. That means ET1 vector equals ET2 vector is 0. Things become more simpler now. And that normal thing is still present, right? Normal component, we will again derive the same thing, that is using the Gauss law. You can derive it. Okay, your normal component will just be the same thing, that is E2, that is the conductive surface, right? If this is, let's say, medium 2 and this is medium 1, both will have only like normal components only. E2 will be equals to E2n, okay, which will be equals to what? Which will be, what can you tell me, what will be E2n? If I have a surface charge density of infinite sheet of perfect conductor, it will be what? It will be simply rho S by epsilon, because what is the charge enclosed in this? Like what am I doing? I'm just finding out the charge enclosed in this perfect conductor, right? I'm just finding out the charge enclosed in the perfect conductor. So how do I find out the charge enclosed? So what you have to identify is that what I can do is I can use the Gauss law again. In this. I will use the Gauss law. So here, if I use the Gauss law just on the surface, what do I observe is that I have a charge density of rho s, which will be equals to d n1 vector minus d n2 vector, correct? Dot a n cap. So this is the relationship, and this is same as writing E1 vector, not E1, sorry, D1 vector minus D2 vector, because it doesn't have any tangential component, it has only normal component. So I can directly replace dn1 and dn2 with d1 and d2, correct? So now what do I know about dn2 or en2? E2n I know electric field will be rho s upon 2 epsilon. For an infinite sheet, I know electric field will be rho s upon 2 epsilon. That will be same as d1 as well, right? And E2n, if I know E2n, I know E2, because E2n and E2 are same only, that is rho s upon 2 epsilon en cap and what about d2? D2 will be simply rho s by 2 n cap, and it will be now so what will be my other electric field? It will be also rho s by 2. Okay, it will be also rho s by 2, because rho s by 2 can like rho s minus rho s by 2 is rho s by 2. Okay, that's why. So I hope you understand this point. So we'll solve one question from here, we'll understand this a better way. So region y less than 0 consists of a perfect conductor. while y greater than 0 consists of a dielectric medium with epsilon r1 equals to 2. So again I will draw the plane region. So y less than 2 and y greater than 2, right? So it will be here. Okay, yeah, x z. So this is the region basically. Now y less than 0 is the conductive region. This is the medium 1, which is conductor, and this is the medium 2, which is dielectric. If there is a surface charge of 2 nanocoulomb per meter square on the conductor dielectric boundary, then calculate the electric field and D at each points 3, -2, -2 and 4, 1, 5. So this is on the surface y equals to 0. So where does my 3 -2 2 lie? So if I observe right here, y equals to -2, y equals to -2. So this will be this A point. A will lie behind the surface. A will lie behind the surface, and what about B? B lies above the surface. So B lies in front of the surface. Okay, so B lies in front of the surface, A lies behind the surface. Now what do I know? If this whole thing, right, if this whole region y less than 0 is conductive surface, I know that my electric field inside conductor will be simply 0. Okay, electric field inside conductor will be 0, that I know. So obviously electric field on point A will simply be 0. Simple. Electric field on point A will be 0. What about electric field on point B? How do I find out? Electric field on point B. Electric field on point B is in front, right? So what is the electric field due to a sheet of like infinite sheet? Okay, infinite charge sheet. It is rho s, the charge on the sheet, divided by 2 epsilon. Okay, plus rho s by 2 epsilon. Now why is there plus rho s by 2 epsilon? That I will explain. So if I have a conductor like this, right? If I have a conductor like this, then I like you are telling on the surface I have charge rho s, correct? So if this is an infinite conductor, on the other side of the surface, right, on the other side of the surface I will have another charge rho s. So although inside the conductor the charge will be 0, but due to this rho s, right, again I will get exert electric field here as well, right? I will get electric field here as well. So I will get electric field due to the 2 rho s, 1 rho s here and 1 rho s here, right? 2 electric fields. So this I know this is a bit confusing. Try to like understand a bit. Here I have 2 rho s. This is a whole volume of surface. Okay, this is not just an infinite sheet. This is not just an infinite sheet. This is a whole conductor. So not a sheet. This is not a sheet. This is combination of 2 sheets. So this direction will be again outward, that is normal to the surface interface medium, that is AY. So this will be rho s by epsilon to AY actually. And what is my rho s? Rho s is 2 nanocoulomb 10 raised to power minus 90, and this is 8.854 into 10 raised to power minus 112 into 2 actually. Epsilon r2 is 2, right? Yeah, epsilon r1 is 1, epsilon r2 is 2. So this comes out to be I will say what this comes out to be. I'll just quickly compute it. Two gets cancelled, and a 10 cube divided by 8.854. This is almost 113. So my electric field on the point B, right, is not half of this. It is actually 113. So many students will make this mistake. They will make the mistake as they will write the half expression of this. That is not the case. This is not an infinite sheet. And to explain you that concept, I am giving you this as homework. Okay, this question you try as homework, and in the next lecture I will solve this question. This is the last question of this lecture. Try it out. Find out the electric field between the two metal plates and outside as well. Okay, so I will give you another expression. All these are charged plates only, and in between I have dielectric. And third expression I will give. Okay, both of them are plus. Okay, this like both of them are plus. Just hold on. Okay, if I can simply do this, right? Both of them are plus. Like both of them are plus, find out the electric field on medium between two plates and outside as well. Okay, so this whole arrangement, right? Where did I go? This whole arrangement you can assume as basically a single conductor. Okay, single conductor with charges all around the surface. Okay, this you assume as single conductor. So yeah, in the next lecture I will solve all this question, and we will start with a new topic, that is method of image charge. Thank you for watching and happy learning.